The first several parts of this lecture dealt with transpiration and its control from leaves. And this last piece, I'm going to go over transpiration at larger scales from either individual trees or from entire forest stands. Now, clearly, the mechanisms which control transpiration from leaves also apply at the whole tree or stand level. But there are different technologies that are used to measure transpiration at those levels, and there also are a couple of different ways of thinking about some of the concepts at the tree and stand level that I think it's useful to talk about. So starting at the whole tree level, this graph, this actually shows daily sums of tree sap flow, which is roughly or pretty closely equivalent to daily transpiration. From individual trees. So each point on that graph is an individual tree, and its daily water loss is plotted against its size, in this case its basal area. These particular data are from my dissertation work, which was, there's a picture of the basin where this was taken. This is in Pacific silver fir, Abies amabilis, in the Cedar River watershed, which is the watershed for the city of Seattle. We used instruments that are inserted into tree stems called sap flow gauges. And there are a number of different theories and types of instruments and types of sap flow gauges that are used, but they all use heat in some form as a tracer to measure the movement of water past the sensors. Now, there's a lot of literature on sap flow and a lot of information on how to properly scale those sap flow measurements. But in reality, sap flow gauges have been a really important emerging tool over the last 25 or 30 years for measuring water relations of individual trees. So they make a nice integrative measurement of physiology at the whole tree level. So they've been very useful in that way. This is another type of sap flow gauge. This particular one is a Granier heat dissipation probe. Inserted into a slash pine tree. Basically, there is an upper and a lower probe. The upper probe is heated. The lower probe is not, and it serves as just a reference temperature. And sap flow, in this case, sap flow is roughly proportional to the temperature difference between those two probes. Basically, as the temperature difference gets closer, or as the sap flow gets larger, the temperature difference gets smaller. And it's a nonlinear relationship, but it's been the relationship between delta T and sap flow is found to be fairly robust for a range of species. So there's a number of technologies that can be used to measure sap flow. This is an example of some of the type of data you can get from sap flow. This shows sap flow from 1, 2, 3, 4, 5, 6 trees of different size in that stand I showed you earlier on 2 different days. The 2 lines show transpiration rate of those different trees on a warm, dry day and a cool, wet day. So they show a couple of obvious things. Tree sap flow, in this case, and in most cases, is strongly correlated with tree size. that's mainly due to the fact that larger trees have more leaf area and therefore can transpire more water. One of the reasons that this relationship is so good with tree basal area, which is just a cross-sectional area of each of those trees at breast height, is that tree basal area is closely correlated with leaf area. So that ends up being a good surrogate for leaf area. So clearly the correlation is strong between the amount of water lost and tree size or tree leaf area. The other thing you note then, of course, is that there are big differences in the amount of water lost depending on weather conditions on that particular day. So in general, on a warm, dry day, you'll get a lot more water loss than you will on a cool, wet day, mainly due to differences in both radiation and vapor pressure deficit on those types of days. You'll note that there's a couple of trees here that are excluded from those regressions where they didn't fit on the lines. We took a look at those trees when we looked at the data and saw that they had, it was one tree, and that tree had a root pathogen. So in this case, that root pathogen was inhibiting that tree's ability to take up, transport, and transpire water. Another thing to note is just the magnitude of water loss from these trees. You can see that, for instance, the biggest tree, which is a half square meter in cross-sectional area, which is a pretty good sized tree, it lost about 300 liters of water on a warm, dry day. So large trees can transpire a lot of water, hundreds and hundreds of liters of water in a day, whereas some really small, in this case suppressed trees, even on a warm, dry day, may lose very little water, on the magnitude of maybe 5 to 10 liters of water, even on a high evaporative demand day. So there's lots of variation in the amount of water loss depending on the tree size, but it can get really large. Here's an example of another type of data that can be derived from sap flow data that's pretty powerful, and that's crown conductance. So this G crown on the y-axis there, that is crown conductance. And conceptually, crown conductance is the sum of individual leaf conductances of all the leaves on the tree. So, hopefully you looked at the optional lecture that showed how the mathematics of all this works. But if you have a tree, and this is a simplified tree with a few leaves on it, each of those leaves has some leaf conductance, which is just the inverse of the leaf resistance that we've talked about. So, and it's essentially the stomatoconductance of that leaf. Recall that conductances in parallel or resistances in parallel are additive as conductances. So if you just take the conductance of these individual leaves and add them up, that will give you the total conductance for that tree. So that gives you both physiological information about the function of that tree, because as the stomata on average close or open, that will change the crown conductance of that tree. But it also gives you something about the architecture of that tree, because the more leaves there are, the greater the crown conductance will be. So for instance, comparing crown conductances under similar environmental conditions between trees tells you something both physiologically in terms of the degree of openness of the stomata, but also something about their leaf area. So this is a really powerful approach for understanding function of an entire tree. In this case, we've plotted crown conductance versus vapor pressure deficit and net radiation. So you can see the positive effects of radiation on this axis, where crown conductance increases with that axis, but is simultaneously reduced as vapor pressure deficit, or the dryness of the air, goes up. So it shows the interaction of those two environmental factors and how they influence crown conductance of this individual tree. So I think this is one of the more important advances that we've gotten through the use of sap flow, is we can derive this type of large-scale data, physiological information from individual trees. So I think that's pretty powerful. So moving up to the stand scale, when we're thinking about stand scale transpiration, there's a couple of commonly used approaches. One would just be to scale or integrate sap flow data. So if you, for instance, measure a number of trees in a stand over time and calculate transpiration of those individual trees, and for instance, like in the graph I showed you previously, relate transpiration rate to tree size, you could then take an inventory of the stand and scale those sap flow data up to the stand level and get an estimate of the total amount of water transpired by a stand. There are different ways to do that. You can scale by tree size. You can also scale by sapwood area. There's a number of approaches in the literature. But regardless, sap flow can be used to derive transpiration. Another approach is to use eddy covariance. And that's what's depicted in this photograph. Eddy covariance uses two instruments. One is a sonic anemometer, and the other is an open path. In this case, this is open path. It doesn't have to be open path. Infrared gas analyzer, ERGA. Those instruments used together can calculate flux, the movement of water vapor and CO2 from a large patch of vegetation. So in this case, we can use those to measure evapotranspiration from the upwind patch of vegetation from these instruments. Now, it takes a lot of calculations, a lot of environmental physics to do this, but this is a really powerful approach. It's large scale. It's measuring an entire ecosystem. Now, note that I said evapotranspiration. This measures evapotranspiration, which is not just transpiration. So it's evapotranspiration, which basically is the sum of transpiration of plants plus evaporation from surfaces. Okay, so it's not just transpiration of plants upwind, it's also any evaporation from surfaces that might include bodies of water. It could include evaporation from the soil. It could include evaporation from surfaces of leaves So after a rainstorm, for instance, or after dew, leaves are wet, and that water evaporates, and that would be measured by a system like that. That last one, evaporation from leaf surfaces, of water from leaf surfaces, would be termed, if it's rainwater that's being evaporated, that would be termed interception loss. Okay, that's sort of going off on a tangent, but I'm just trying to make it clear that the measure from eddy covariance is not the same as the transpiration, the leaf transpiration we've been talking about, or the scaled up sap flow that you would get to measure stand transpiration. Now, often sap flow measurements are used in combination with eddy covariance because now you have a large measurement, that eddy covariance, that gives you evapotranspiration, and then you can use the sap flow to get this part, at least for the trees, and by subtraction you can find out what part of your measurement is due to evaporation from surfaces. So often these types of measurements are used in conjunction to get additional information about function. But regardless, eddy covariance is a really powerful approach, and it's really exploded as an approach in ecology in recent years.